All right, in section 2.3.1, the journey begins, the journey being the journey towards calculus. So the tools we've learned, especially with summation notation, we're going to combine with what we know about functions to get at something called area under the curve, and that's what we're going to explore today, area under the curve. So the notes that I'm going to show you are from 2.3.1. They'll go at the top of your flipbook in that section. And I'm not going to do any examples for this. I'm more going to define a notation for you that's going to allow us to do some answer some questions in class, and really focuses on how to read the math. So next year when you see it in calculus, you'll be ready for it. So this will go at the top of your flipbook in section 2.3.1, area under a curve. And we're going to sketch, first going to look at the graphical approach to this, and then we'll look at the notation written for it. So let's say we have a curve that looks like a cubic. And we want to just look at a part of this cubic on the domain A to B. What we're going to end up doing is we're going to restrict the domain using A and B. And we want to be able to find the area under this curve, which we'll explore a lot in Chapter 2, this shaded area. Everything under the curve and until you hit the x-axis, so between the curve and the x-axis on the domain A to B. Now the question becomes, how do you write this? So the notation for this, the math language looks like this. A, parentheses f of A is less than or equal to x, which is less than or equal to b. And this is what you'll see in calculus, and you'll see on one of my tests, this notation, which is, if you can figure out what each part means, then you can figure out what it's asking. So the A just represents the area. The F, and maybe I'll help here if I label this F. This is our F of x. That's the curve itself. Our F represents the function, or the curve we're dealing with, which can change. And this inequality notation is your domain, which we've been writing in interval notation as A, comma, B. So if we read this from left to right, what this is asking is find the area under the curve of function f on the domain A to B, or in other words, the area of this shaded region. We will be using this notation to help us answer questions throughout 2.3, and we're going to look at how to find the area under the curve, different methods for doing that. All right, now to go back in time a little bit, if you go back to your flipbook in 2.2.2, there are a couple notes I want to give you that go over some terms that might seem random, or some concepts that might seem random, but that are actually going to be really important for us. The first one, this will go on the top, or actually the bottom left, is called subscript notation. And subscript notation is another way of writing something. So we're going to use inequality for it. So let's say 2 is less than or equal to x, which is less than or equal to 4. You can also think of this as your domain. So, or, for those of you like the interval notation, you can think of it as 2 comma 4. So on this interval, what we're going to end up doing when we're looking at the area under this curve from, say, A to B, is we're going to divide it up. So let's actually call this first number 2 and this last number 4. That's the domain we're looking at. Let's say we want to divide it up into different pieces. Divide it in half and divide the half in half again, just kind of approximate. So if we divided this in half, we get 3. If we divide the half in half again, 2.5 and 3.5. So now we're kind of breaking up this domain into 4 different equal sections. we're going to refer to each of these as x sub 0. Oops, let me zoom in here. X sub 0, x sub 1, x sub 2, x sub 3, and the last one will be x sub 4. Now, if you look at how many pieces are here, you can tell that there are 4 equal pieces. But there are 5 divisions. So 4 equal pieces and there are 5 divisions. Meaning we are starting at x sub 0 and we're going to x sub 1. There will always be one more division than pieces. Okay? That's kind of important to note. So you can see we have, again, we have 1, 2, 3, 4 equal pieces with, if we label our divisions, we have x sub 0, x sub 1, x sub 2, x sub 3, and x sub 4, 5 divisions. Okay, so that's kind of a way of understanding it. The second part of this is going to be totally unrelated, but will become important later, so we're going to introduce it now. It's called adding rational expressions, and this is something you saw in the summer packet and might have seen in Frank's class a little last year too. So adding rational expressions. And the key to this is you have to find a common denominator or an LCD. Find an LCD. So we can write denominator below that just to define it. So we'll look at an example here. I know this seems completely unrelated to subscript notation. That's fine. It is. There's no real relationship, but it will become important later. So we'll look at an example. So let's add the rational expressions. So here we have it. We'll say 2 over x plus 2 plus 3 over x minus 1. Alright, the problem with this is right here. We don't have common denominators. So we need to do something about that. We need to find the LCD. Now the LCD is actually going to be whatever our denominator is. So it's going to be, if we want to define it, x plus 2 and x minus 1. That's going to be our end product. So we're going to multiply actually here by what's missing. So on the right, we are missing x plus 2. But since we don't have, actually, let me take this away so we have some room here. Since we don't have an equation here, we can't just multiply by x plus 2. We'll have to multiply by x plus 2 over x plus 2, because this is equivalent to the number 1, which signifies that you're not really changing the value of something, you're just changing the way it looks. We're going to do the same thing with the other side. We're going to multiply by what's missing. Here it is x minus 1 over x minus 1, which is also the same as the number 1. Now we can go ahead, by doing this, we're going to multiply across on both of these. So distribute the 2 and distribute the 3. Leave the denominators the same. So we'll get 2x minus 2 over x minus 1 times x plus 2 plus 3x plus 6 over x minus 1 times x plus 2. Now, our denominators are the same, which makes our life nice and easy. If that's the case, we can combine our like terms, which is the 2x and the 3x, and the negative 2 and the 6. So for our final answer here, 2x and 3x would be 5x plus 4, and all of this is over. You don't need to FOIL this out. You can leave it like this, and the reason we want to leave it as binomials is we want to see if anything cancels. So in our final product, nothing ends up canceling after we combine, so your final answer will be 5x plus 4 over x minus 1 times x plus 2. Okay. Now, I know this is random. You will see more of this later, so we're just going to introduce it now as a way of kind of reviewing Algebra 2, but also kind of a preview of what's to come.